In the previous video, we introduced the Bode diagram for the first order and second order transfer functions, and we reviewed some of the key features. In this video, we'll look at the Bode diagrams for some additional types of transfer functions. Let's start with an easy one, the integrator. The integrator is a gain divided by s. We can find the frequency response by substituting s equals j omega. The amplitude ratio is the square root of the sum of the squares of the real and imaginary parts. Now, when we substitute s equals j omega, we end up with a j omega in the denominator, and we can resolve this by multiplying the numerator and denominator by the complex conjugate minus j omega. When we multiply by the complex conjugate, we end up with only an imaginary part with a j in the numerator, minus j times k divided by omega. So the amplitude ratio is k divided by omega. To find the phase angle, we need to take minus the arctangent of the imaginary part divided by the real part, which is minus the arctangent of infinity, or minus 90 degrees. Now that we know the amplitude ratio and the phase angle, we can prepare the Bode diagrams. To get the normalized amplitude ratio, remember we divide the amplitude ratio by the gain k. So you can plot the normalized amplitude ratio as a function of omega tau on this log-log plot, and the phase angle as a function of omega tau on this semi-log plot. Take a moment to do that and then see if your plots look like mine. The semi-log plot of the normalized amplitude ratio is a straight line with a slope of minus 1 that goes through the point 1, 1. And of course the phase angle is independent of omega tau. It's a constant at minus 90 degrees. How about for a time delay? To find the frequency response of the time delay, we need to substitute s equals j omega into the transfer function for the time delay, e to the minus s theta. When we substitute s equals j omega, we get e to the minus j omega theta, which can be written as cosine omega theta minus j sine omega theta using the Euler identities. This is already divided into the real and imaginary parts. To find the amplitude ratio, you may recall that cosine squared plus sine squared is equal to 1. So the amplitude ratio for the time delay is equal to 1. That means that the amplitude of the output will always be equal to the amplitude of the input. But because the output is delayed in time, the phase angle is non-zero. To find the phase angle, we need to plot cosine omega theta minus j sine omega theta in the complex plane, starting at omega equals 0 and increasing omega. Now, the real part, cosine omega theta, clearly must oscillate between 1 and minus 1. Similarly, the imaginary part, minus sine omega theta, also oscillates between minus 1 and 1. Because the real part is on the x-axis and the imaginary part is on the y-axis, this trace just circles the origin around the unit circle in the clockwise direction as omega is increased. And as omega gets larger and larger, we encircle the origin multiple times. This means that the phase angle is becoming more and more negative, and it passes 360 degrees and keeps becoming negative. It goes around the origin from the point 1, 0 to the point minus 1, 0, and then it continues back to the point 1, 0, and then back to the point minus 1, 0, back to the point 1, 0, etc. Meaning that the phase angle is continuously decreasing as omega increases. Now you prepare the Bode diagram by plotting the normalized amplitude ratio and phase angle on these plots, and see if they match the ones that I've produced. The amplitude ratio, or normalized amplitude ratio, is equal to 1 for all values of omega tau, and the phase angle decreases as omega tau increases, and approaches minus infinity as omega tau goes to infinity. Next, let's look at a 0. A 0 is a tau s plus 1 term in the denominator of a transfer function. By substituting s equals j omega, we find that the 0 is already divided into the real and imaginary parts, and the amplitude ratio is the square root of omega squared tau squared plus 1. while the phase angle is the arctangent of omega tau. A left half-plane zero with a tau greater than 0 is called a lead element because it makes the output lead the input, that is, the phase angle is greater than 0. As the frequency omega gets large, the amplitude ratio increases linearly with omega, regardless of whether it is a right half-plane zero or a left half-plane zero. That is, it doesn't matter what the sign of tau is. But the sign of tau does affect the sign of the phase angle. If we combine a left half-plane zero with a left half-plane pole, we have what we call a lead-lag element. Now you can understand why this is called a lead-lag element. The numerator term causes the output to lead the input, while the denominator term causes the output to lag the input. In the next video, we'll show how we can combine first and second order transfer functions with zeros, time delays, and other elements to obtain frequency responses represented by Bode diagrams for more complicated transfer functions.